Okay, here we are back for the second video lecture for chapter 14. So now we're going to start talking about what are called significance tests. Now that we've got all the stuff about confidence intervals and that sort of thing out of the way, significance tests are the next step here. And a significance test is really nothing more than a statistical procedure where we basically sort of evaluate hypotheses. Okay, so for example, as you see here, somebody makes a claim, a hypothesis, let's say, about an unknown population parameter. Typically, the population mean is what we're looking at. We want to check to see whether or not that hypothesis that they've made is supported by the sample data or not. Okay, does that statement, that hypothesis that they've made, make sense given the sample data that we have to evaluate it with? Remember, sample data will allow us to calculate a sample mean, which we can then compare to maybe a true population mean, or at least use to infer something about the true population mean if we don't know it directly, which in most cases we don't. So a test of statistical significance analyzes a hypothesis using sample data to determine whether or not that hypothesis is valid or sound. All right. So let's look at an example, a scenario here that we're going to follow throughout much of this discussion about significance tests. Blood levels of inorganic phosphorus are known to vary normally among adults, okay, with a mean of 1.2 millimoles per liter and standard deviation of 0.1 millimole per liter. All right, so we know that because there's been years and years and years of data taken on this, and we have so much data, we effectively know what the true population values are, those you see right there. But the question is the true mean inorganic phosphorus level something different, maybe lower among the elderly? Okay, the elderly population, say people 72 and older or something like that. Well, we take a random sample, let's say of 12 healthy elderly subjects. We average their blood phosphorus levels, and we see we get 1.128 millimoles per liter. So on the face of it, that is different than 1.2 that we saw up here for the population generally. It's lower, but here's the question. Is that difference that we see there, 1.2 that you see here, minus the 1.128, is that difference due to just chance variation, or is it evidence that the elderly do actually have lower blood phosphorus levels? Right? Remember that everything varies, right? There's natural variation everywhere. So we want to tease apart whether or not that difference that we see here is a real biological effect of the aging process, or if it's just random variation. It could be that tomorrow you take another sample of 12 blood samples from 12 healthy elderly individuals, and you average their blood phosphorus levels, and maybe you see it's actually higher than 1.2. Who knows, right? We want to know, is this difference a real biological phenomenon, or is it just random sampling noise? Okay. That's always going to be the basic question here, right? Teasing apart whether something is a real phenomenon or if it's just random variation. So we have hypotheses here that we're going to look at. And we always have two hypotheses. We have what's called a null hypothesis. This is always denoted as H sub O. This is a specific statement about a population parameter, okay? The alternative hypothesis, which we refer to as H sub A, is usually a more general statement, less specific than the null. It complements the null, but it is mutually exclusive with the null. That means that if one of these hypotheses, let's say the null is true, the alternative can't be true. If the alternative is true, the null can't be true. So they are mutually exclusive, but they do complement one another. So for this scenario that we're talking about with the elderly and their phosphorus levels, the null hypothesis here would be that their population mean is 1.2 millimoles per liter. Okay. The alternative is that the population mean amongst the elderly is less than 1.2 millimoles per liter. And presumably, this might be due to some aspect of physiology that changes as we age. Okay. All right. Next thing we have to deal with is figuring out whether or not we're dealing with what's called a two-tailed hypothesis or a one-tailed hypothesis. Okay, so let's say that we have a sampling distribution curve here, okay? And we know that, again, oops, we have our mean right there. That mean of that sampling distribution should match the mean of the population distribution, okay? If we are dealing with a two-tailed situation or a two-sided alternative, okay? And by the way, these different hypotheses, two-tailed versus one-tailed, they always concern the alternative hypothesis, never the null, okay? So if we're dealing with a two-sided alternative hypothesis, it's very possible that we could expect that our sample mean would fall above or below the true population mean. We're not stating that it can only fall less than or can only be greater than. We're basically giving the option of it to be both, or either one. It could actually be greater than or less than. In other words, we're dealing with both tails of the curve, the positive side and the negative side. That's a two-tailed or two-sided alternative, okay? So basically, if you see an alternative hypothesis stated and you see the symbol not equal to, or you see the words not equal to phrased, that's an indication that you're dealing with a two-tailed situation, as we'll see more about here in a little bit, okay? Now, what about a one-tailed or one-sided alternative? Well, in this case, this is going to be asymmetric, and we're dealing with only one side of the curve. So maybe it's the case that we're only allowing for the possibility that our sample mean could be greater than our population mean. So it would only fall to the right. In that case, we're only dealing with this side of the curve. It's a one-sided or one-tailed alternative, okay? So in your alternative hypotheses, when you see them stated, if you have a greater than sign or a less than sign, that tells you you're dealing with only one side of the curve or the other. So it's a one-sided alternative. So what is it then that determines our choice of one-sided versus two-sided? Well, it has to do with, the experiment you're doing, the study you're doing, the questions you're asking, that sort of thing. And it has to do, obviously, with what you know about the problem, importantly, before performing the test. We always have to have this worked out and figured out before we actually design our experiment, or as part of designing our experiment, before running our experiment, before collecting our field data, because otherwise we can introduce bias, right? So if the question or problem is asymmetric, then the HA should be one-sided. If it's symmetric, then the alternative should be two-sided. And so let's look at some examples to try and clear some of this up. All right, example number one here is the active ingredient concentration as stated on the label. So if the label says it's 325 milligrams per tablet for some drug, maybe ibuprofen or whatever, our null hypothesis is that the concentration of the ingredient, active ingredient, is 325. The alternative is simply that it's not. So by using the not equal to sign, we're not stating specifically that it's greater than or less than, we're just saying it's not equal to, which implies it could be greater than or it could be less than. So that is two-sided, okay? Second one, is nicotine content greater than the written 1 milligram per cigarette on average? So here's our null, which is that the nicotine content is equal to 1. The alternative is that it's greater than. So we're only allowing for the possibility that it's greater than, so that's going to be one-sided. Third, does a drug create a change in blood pressure on average? So it just says a change, right? A change could be positive or negative. So here you see the not equal sign. So that's going to be two-sided. All right. And in this case, the null would be 0, right? Does a drug create a change in blood pressure? If it doesn't create a blood pressure, it's not changing. If the change is 0, that's why you see 0 there. All right, fourth one. Does a particular stream have an unhealthy mean oxygen content, a level below 5 milligram per liter? Let's just look at that first statement. That's our hypothesis. They are only one statement, okay, one sentence statements. Our null is that it's equal to 5 milligrams per liter, and the alternative is that it's less than. Why less? Because it says unhealthy, a level below 5 milligram. So we're just concerned about the left-hand side of the curve. So again, we see one-sided. Now, what about the second statement here? Ecologists collected a liter of water from each of 45 random locations, blah, blah, blah. That's just extraneous information, okay? An alternative hypothesis or a null hypothesis statement is just a single sentence statement, as I said. Also, we never include sample data, you see an average there for a sample in our hypotheses, because that implies that we're actually forming our hypotheses after we've collected our data, and that's backwards. We always form our hypotheses first. You don't want to cherry pick your data and say, well, my data better supports a one-side hypothesis rather than a two, so I'll go with a one. That introduces bias. So we would never include any sort of sample data in our hypothesis because our hypothesis is developed before we even collect any data. All right, so let's talk about the p-value. So p-value is a really important concept in statistics today, and I'll tell you that this is one concept that, in my experience teaching this course, students sometimes go all semester long from this point on never really understanding. And that's to their detriment because you're going to see p-values in every lecture from here on out. Okay, so you've got to understand what it is. All right, so go back to our phosphorus levels example. Again, we know that phosphorus levels vary normally, standard deviation of 0.1 millimole per liter. All right, our null hypothesis here is that elderly folks do have a 1.2 millimole per liter average phosphorus level, the same as other adults, younger adults, versus the alternative that elderly adults would have lower mean phosphorus levels. All right, so we know from our sample of 12 that we have 1.128 as our sample average phosphorus level. So the question is, what is the probability of drawing a random sample of, say, 12 adults, mean phosphorus level, and getting a mean phosphorus level as small as this one, okay, 1.128, if our null hypothesis is true? So if the null hypothesis is true, then elderly people do not have higher or lower, and specifically lower, mean blood phosphorus levels than other adults, correct? So if that's true, what is the probability of sampling from 12 elderly adults and getting a mean blood phosphorus level that small, that far below our actual population mean? That probability is what our p-value is, okay? The p-value is the probability, if our null is true, of getting a sample mean at least as extreme in the direction of the alternative, so in this case, lower than the population mean, as the sample mean we actually got. P-value tells us how likely it is to get a sample mean of 1.128 millimoles per liter if the elderly do have a mean blood phosphorus level of 1.2. All right, so this sets up the concept of sort of a threshold, right? If we have our normal curve here, okay, and again we have our population mean, we want to set up basically on either side a threshold value, okay, beyond which, or against which rather, we can compare our sample mean. So if we look at that threshold value, we're going to have some amount of area to the right of that and some amount of area to the left of that. If a sample mean falls to the right, say over here somewhere, of that threshold value, we would assume that that is so unlikely that that sample mean must represent a sample from a different population, not this population, okay? However, if we had a sample mean that fell there, for example, well, that's a lot more likely because if you look at the area to the right of that curve, right, that is a much higher probability of occurring, that sample mean, than one here, for example. So with that sample mean being closer to our true population mean and having such a low probability or a high probability of occurrence based on the shaded area to the right, that's our probability, we would say that that sample mean actually does come from this population. But the point is, we'll see more about that later, but the point is that we have to set up these thresholds, okay? And so the p-value basically is the probability of getting a mean that falls at or beyond to the other side of that threshold value, okay? All right, so let's take a look at this. This is a screenshot from one of the applet simulations that you'll see on Canvas under Chapter 14. You can go there and you can hit that link and you can play with it and manipulate terms and that sort of thing. But this one is geared toward this hypothetical example we're talking about with the elderly adults and their phosphorus levels. So we know we have a mean of 1.2. Our alternative hypothesis is that the elderly phosphorus levels are less than 1.2, we know we have a standard deviation of 0.1, sample size of 12. So what we have here is our sampling distribution, right? So remember, there's going to be a population distribution that sort of overlaps this, but it's wider. It will, however, have the same mean of 1.2, all right? So we have a sample mean of 1.128. And this blue line is showing you where that sample mean falls on this x-axis of blood phosphorus levels, okay? We're concerned about the area to the left. So if you calculate the z-score based on 1.128 as a sample mean, given this sample size and that standard deviation, as we've done already, you look up that z-score on the table B, and you see the area to the left of it ends up being 0.0063. That's our p-value. You take that number, multiply it by 100 to convert it to a percent, and you see that the area to the left of that is 0.63% of our curve. Areas are probabilities. We've talked about this, right? And so that means that a sample mean of 1.128 falling there has a 0.63% chance of occurring. That's a pretty small chance, right? Okay. Typically, that is going to lead us to believe that the elderly do not have the same mean blood phosphorus levels as other adults, okay? The elderly would actually have lower mean phosphorus levels. And so what we need to do is set up a threshold, and typically our p-value, if it's less than 0.05, then we say that it is significant. We say that that mean that has a p-value less than 0.05 represents a sample that is actually different, a sample mean that is actually different from our true population mean. So we have to define that cutoff point where basically we have 5% of our curve right here, okay? That cutoff point right there is called alpha, okay? Alpha, or the significance level. All right, so let's say that we're doing 95% confidence. We're setting our confidence at 95%. That means that our alpha, or significance level, will equal 5%. So the way you calculate your alpha or significance level is that you take your confidence level and subtract it from 1, or 100%. So 100% minus 95% gives you a significance level of 5%. That defines this boundary right here. That's our threshold, our cutoff. So if we get a sample mean that falls, like ours, that falls below that, we know that that sample mean has a less than 5% chance of occurring. In fact, it has a 0.6% chance in this case. And we recognize that as being so far away from our true population mean of 1.2 that it's extremely unlikely to have occurred from this sampling distribution. So the idea here is that with our hypotheses, we're basically saying that if the null hypothesis is true, we have one population. We have one population of adults with regard to blood phosphorus levels, and the elderly are part of that population, which means that their average shouldn't be any different than anybody else's average, okay, or any other group's average in that population. If, however, the alternative hypothesis is true, we're saying that the elderly, with regard to blood phosphorus levels, represent a different population whose blood phosphorus level average is less than the rest of the population, or the other population. So we would have two distinct populations: the general adult population, and then the elderly adults who would have lower mean phosphorus levels, okay? All right, so maybe the sample mean right here actually represents the mean of a different curve, okay? A different sampling distribution which describes a different population distribution, okay? All right, so you need to play around with this applet here to help you better understand this idea of the p-value, okay? And you can see what happens to the size of the sampling distribution if you increase or decrease the sample size. What if you pick a different alternative hypothesis, two-sided versus one-sided, all that. There's a lot you can do with this. So these applets, again, are loaded up on Canvas for you to take a look at. All right. So in this case, we would say that 1.128 as a sample mean for blood phosphorus levels is significantly lower than the population mean of 1.2, the wider population mean of 1.2. All right, so how do we then interpret that p-value? Well, again, the question is, could random variation by itself account for the difference we see between our null hypothesized mean and our sample mean? So small p-values, typically less than 0.05 or less, are strong evidence against the null, and in that case, we would reject the null. We would say that these findings are statistically significant. Okay, statistically significant. Large p-values, typically anything greater than 0.05, would not give us enough evidence that the null is not correct, and we would, well, they say fail to reject, or you could just say accept the null. We would accept the null. All right, now one thing about this, if you accept the null, you're not proving the null to be correct or true, okay? If you accept the null, all you're doing is saying, well, we don't have enough evidence to be able to reject the null, all right? So we never, first of all, say the word prove in science because we never know anything with absolute certainty. We can be pretty certain, but we never say prove. Secondly, if you reject or if you accept the null, you're not absolutely stating that the null is true. You're just stating that you don't have enough evidence to reject it, okay? However, if you accept the alternative hypothesis, that is a more definitive statement about the validity or veracity of your alternative hypothesis. Okay, you are stating that we have fairly high confidence that the alternative hypothesis is actually correct. So what about range of p-values? Well, typically, because we're usually looking at confidence level of 95%, that's the most common, we would have a significance level or alpha level of 0.05. That means p-value of 0.05 is our deciding line, right? Our line in the sand, so to speak. So if you have a p-value of 0.05, you could call that somewhat significant, okay? Or if you have, let's say, a p-value of 0.01, that would be significant. Very significant, maybe 0.001, and then maybe if you have highly significant 0.000 or 0.001, sorry, 0.0001. So basically, for the most part, these are based on orders of magnitude, right? A single decimal place difference is an order of magnitude times 10. So significant or somewhat significant, significant, very significant, highly significant. You very often will see these terms in scientific papers when the authors are talking about their results, and they basically sort of correlate with these p-values. All right, so significance level alpha, as I talked about, okay, is simply this threshold, right? It's our deciding line. It's the largest p-value that we'll tolerate for rejecting the null. In other words, how much evidence we need against the null in order to be able to reject it. And we decide this alpha level before conducting our test, okay? And again, typically it's 0.05, but let's say you need to be really certain about your results if you're going to state that your alternative is, or your null hypothesis is rejected. Maybe you want to be 99% confident, in which case you'd have a 0.01 significance level. So you're looking at a p-value of 0.01 or less for determining whether or not to reject your null hypothesis, okay? Sometimes you see confidence levels of 90%, which would mean a p-value of 0.10. That's pretty rare, but occasionally you see it. Like I said, 0.05 is the most common, okay? And so when p-value is less than our alpha level, we reject our null. When the p-value is greater than our alpha, we accept the null. So if we have a alpha of 0.05, a p-value of 0.12, in that case, we would accept the null. A p-value of 0.03, in this case, we reject the null, all right? So the nice thing about this is that it's objective, it keeps us honest, it brings our decision down to a black and white decision based on a p-value, all right? Okay, so test for a population mean, okay? And this is going to be where, again, we don't typically know what our population mean is, okay? To test the null hypothesis that our population mean here is equal to our hypothesized population mean using a random sample of size n from a normal population with a known standard deviation, we're going to use a null sampling distribution. So again, this is all based on the sampling distribution, right? So sampling distributions can be normal, defined by some mean and some sampling distribution standard deviation. But in this case, we had the 0 there, null 0, because this is our hypothesized null mean, okay? All right, the p-value is going to be the area under that sampling distribution for values of our sample mean that are at least as far away in the direction of the alternative as that of our random sample. So again, we need to calculate a z-score, right? So we take our sample mean, subtract our hypothesized null mean from it, and divide it by our sampling distribution standard deviation, as we've done in previous chapters. So we look at the p-value in a one-sided test here, okay, and two-sided tests. And if we have an alternative that's one-sided, where our population mean is greater than our hypothesized mean, then we're just dealing with this right tail, okay? If we say it's less than our hypothesized mean, we're dealing with the left-hand tail. So in both cases here, this is a one-sided test. If it's two-sided, in other words, you see the not equal to there, we're saying it could be greater than or less than our hypothesized mean. Now we're dealing with both tails. That's why it's a two-sided test. All right. So to calculate the p-value for a two-sided test, you're going to use the symmetry of the normal curve. You would find the p-value for a one-sided test and you would simply double it. All right. So let's take a look. So this is table C that we looked at in the first video lecture for this chapter. Remember, we were looking at our confidence level up here. Okay, so for example, there's 95%. You draw a line down and you get the z-score for that, in this case 1.96. All right. Now, if you look below the z-scores, you see p-values, one-sided p and two-sided p. So at two standard deviations, or roughly 1.96 right here, okay, you would have about 95% of the area of your curve. That's a 95% probability. That's why we have 95% confidence there. Now, if you have a one-sided test, you're just dealing with one side of that, so your significance level would have an area to the right of 0.025 or 2.5%. However, if your sample mean could fall above or below your population mean, then you're dealing with both tails, then it would have a 5% chance of occurring outside those bounds. 2.5% on the right side, 2.5% on the left side, 5% total. This is why for a two-sided test, you double your p-value for a one-sided test. All right. Okay, so let's go look at our example here with the elderly. All right, so question again was, do the elderly have a mean phosphorus level below 1.2 millimoles per liter? Our null hypothesis is that the population mean of the elderly is 1.2, which is a way of saying that they're the same population as the rest of our adults that are not elderly, versus the alternative that our elderly folks have a mean blood phosphorus level of less than 1.2. So what would be the probability then of drawing a random sample of, say, 12 people with a mean of 1.128 or smaller if this null hypothesis is true? All right. Okay, I gotta draw some stuff in here, sorry. Okay, so we know that our sample means 1.128. We know that our sampling, our standard deviation for our population is 0.1, and we know that our sample size is 12. Okay, we also know that X is normally distributed. So our z-score calculation then is z equals X minus mu 0, okay, 1.128 minus 1.2 over our population standard deviation of 0.1 divided by the square root of our sample size. So you do all that math, you get a z-score of 2.494, actually negative 2.494. In table B, you'll look up negative 2.494, and it gives you an area to the left of 0.0064. That's your p-value. Multiply that by 100, and it's 0.64, okay? That tells you that a sample mean of size 12 of 1.128 has only a 0.64% chance of occurring if the elderly do have the same mean phosphorus levels as the rest of the adults in the population. All right. Now, Table C will bracket that for you, where Table B will calculate, or you can find the p-value directly. Table C brackets it. Okay, so on Table C, and I'll show you this in a moment, a one-sided p-value is between 0.005 and 0.01, and our p-value falls between those two numbers, doesn't it? You would use the absolute value of z here on this table, and I'll show you that in just a minute. So the probability of getting a random sample average that is this low, this much below 1.2 is so low, 0.64% chance, that we would reject our null. Anything, in this case, below 5%, or 0.05, our alpha, we would reject. And that is certainly a lot below 0.05, right? Okay, so the mean phosphorus level then among elderly is significantly less than 1.2. It falls so far over here that this difference that we're seeing between it and our true population mean is very unlikely just to be due to random sampling variation. It's most likely a biological effect, and so that's what we're going to say. By rejecting that null, we're saying it's a biological effect. We're saying that the elderly do actually have lower blood phosphorus levels than the rest of the population. All right, let's look at Table B. We've got to look up a z-score of minus 2.494. All right, so here you see it. So we have minus 2.4 over here on the left. Minus 2.49 is right there, and you see our p-value is 0.0064, okay? Doesn't go any further off the table, 0.094, for example, so we're going to go with that. Now, Table C, we want to be 95% confident, all right? And so we had a one-sided p-value of 0.006, and so you look on the bottom, right? So you follow this line over, and you see we have our p-value falling between 0.005 and 0.01. That means that we are between 98 and 99% confident that that the elderly do have lower blood phosphorus levels on average than the younger adult population. Okay. All right, I think we'll stop there. I've just got a handful of slides left to finish up for the third video lecture, but I think that 40 minutes or so, which is about how long I've been going, is good. So we'll finish this up with a fairly short, I think, third video lecture on this.